Finally, you're ready to finish your proof of the fundamental theorem of arithmetic by showing the uniqueness of each prime factorization. In doing so, you'll find the result we just proved. Let's call it the useful result, to be, well, useful.
So if the prime q is the divisor of a product of a list of primes, then it must be one of the primes in the list.
Yes, exactly. So the next question is, exactly what statement should we prove in order to assert uniqueness?
Pretty simple, actually. You just prove that if it's a prime factorization, then it's the only one.
Brilliant, Ron. That's a big help.
We've talked about how mathematicians go about proving that something is unique.
Is it where you assume there are two different things and then show they must be the same?
That's right. So what two things should we start with?
Maybe two different prime factorizations for the same number?
I agree. Can we start to be more specific? By which I mean, can we give names to the things we're talking about?
I'm good at making names. Let's call the natural number...
Be sensible.
Oh, all right. K. Which is short for kangaroo.
Oh boy.
Tell me about K.
It has two prime factorizations?
Let's take them one at a time.
So the first one could be P1, P2, P3, etc.
You have to know where to stop. P sub something.
That's right. We need a variable for the number of primes in the factorization.
How about A?
Okay.
For Australian common wombat.
I'm sensing a certain theme here.
So the primes are P1, P2, and so on, up to PA.
What else can you say about the primes P sub 1, P sub 2, and so on?
If you multiply them together, you get K.
Very good.
Also, aren't they in non-decreasing order?
Yes, and that's very important. Let's say P sub 1 is less than or equal to P sub 2, and so on, is less than or equal to P sub A. So far, so good. Now let's think about the second prime factorization.
So that would be Q1, Q2, through Q sub
B for Australian long-nosed bandicoot.
through Q sub B.
Okay.
So they multiply to make K.
And they're in non-decreasing order.
Now, given these two prime factorizations, what do we need to prove?
That they're the same.
If they're the same, then A and B are the same because each list has to have the same number of primes.
And what else?
So for every I, P sub I equals Q sub I.
And I is between?
I is between 1 and A, or B. It doesn't matter, since they're the same.
Good. Now, not surprisingly, you will need to prove this by induction. To do that, you need a clear statement that you will prove is true for all natural numbers bigger than 1. So I'm going to help you by suggesting you start like this. The idea is to show that each natural number k from 2 through n has a unique factorization. This seems to introduce an extra layer of complication, but it turns out that it simplifies the induction step. The good news is that once you've proved this, the proof of the fundamental theorem follows in a very trivial way, just as it did when we proved existence. So we'll show that if the natural number k is between 2 and n, then it has the property that if for some natural number a, and some collection of primes p sub 1 through p sub a, in non-decreasing order, k is the product of those primes. And if for some natural number b and some collection of primes q sub 1 through q sub b in non-decreasing order, k equals the product of those primes, then a and b are the same, as are each p sub I and q sub I. So, can you prove the base of induction?
The base is the statement p sub 2?
Yes.
So then k has to be 2, and the only collection of primes whose product is 2 consists of the prime 2 and nothing else. So obviously, a and b are equal to 1, and the only p sub I and q sub I is 2, so obviously they're equal.
And so you prove the base. What happens next?
We would use m.
For marsupial.
So suppose m is a natural number greater than 1.
So big P sub m is the induction hypothesis.
So you know that every natural number from 2 through m has the desired property. So now you only need to show that m plus 1 also has the property.
So suppose m plus 1 has prime factorizations of the p's and q's.
Focus your attention on p sub 1, the smallest prime in the p list. What can you tell me about it?
It divides m plus 1.
Exactly. And of course, m plus 1 is equal to q sub 1 times q sub 2 and so on.
So p1 divides the product of q sub 1 through q sub b. Oh wait! What did the useful result tell us?
That's right. P1 divides the product of the q's, so it must be equal to one of them.
Good. P sub 1 divides the product of the q's, and so it must be equal to one of the q's. That is, p sub 1 is equal to q sub I for some I from 1 through b. At this point, I'll give you a small hint. Since p sub 1 is q sub I, and the smallest of the q's is q sub 1, it must be that q sub 1 is less than or equal to q sub I. That is, q sub 1 is less than or equal to p sub 1.
That's not much of a hint.
You could just use the same argument, except swap the p's and q's, and you would get that q1 is less than or equal to p1, and you'd have proved that p1 equals q1.
Excellent.
Okay, so maybe it wasn't a terrible hint.
So, you prove that the first prime in each list, p sub 1 and q sub 1, are equal. Now what?
Oh, I know. I just need another hint before I can say it.
Okay. We need to find a way to bring the induction hypothesis into play. And the easiest way I know to do that is as follows. First, consider the case when a is equal to 1.
So if a is 1, then there's only one prime in the list, namely p1.
Which is equal to q1.
Right, equal to q1, and so q1 equals m plus 1. So q1 is equal to the product of q1 through qb.
I think maybe b is also 1.
Well, if b is greater than 1, then we could cancel by q1, and so 1 is equal to the product of q2 through qb. But there's no way to multiply primes together and get a result of 1. Since that's impossible, it must be that b is not greater than 1.
And so b is also equal to 1.
Good so far.
Also, if b is 1, then a must be 1, and the list of primes is just p1, which equals q1.
Correct again.
So are we now supposed to figure out what happens if a and b are more than 1?
Yes. And note that this means that m plus 1 is equal to p sub 1 times p sub 2 through p sub a. And since p sub 1 equals q sub 1, that's equal to p sub 1 times the rest of the q's.
We can cancel the p1s, So the product of P2 through PA equals the product of Q2 through QB.
That's right. Note that the P1 is greater than 1 because it's a prime, so the product of P2 through PA is less than m plus 1. And since it's a product of primes, it's also greater than 1.
I think I see where this is going. So the product of P2 through PA is a natural number from 2 through m?
Yes, and the same would be true for the Q's.
So you can apply the induction hypothesis?
Yes, at least I think so.
You can, in fact, apply the induction hypothesis at this point. It's a little tricky because the number of primes in the collections P sub 2 through P sub A and Q sub 2 through Q sub B are A minus 1 and B minus 1 respectively. So it gives us that A minus 1 equals B minus 1, and that corresponding P's and Q's are equal. You already know P sub 1 equals Q sub 1, and now you know all the other corresponding P's and Q's are equal. And since A minus 1 equals B minus 1, you know that A equals B.
And that proves the statement big P sub m plus 1?
It does. And so having proved the base, the induction proof is complete. So, to wrap things up, we take what we have just proved and use it to prove the uniqueness property.
So we just proved that every natural number between 2 and n has the uniqueness property, right? So it seems to me that n is a natural number between 2 and n. So obviously, it has the property.
I thought you were asleep.
I think I'm going to study that induction proof.
Me too.
Me 3.
Me hungry. Emmy, got any of those cookies?
Yes, it's quite complicated. It may take 2 or 3 cookies to work your way through this last part. So, grab some cookies and make sure you read it. Well, slowly and carefully.